Hello everyone, November 30th. Alright, let's get this done and go back to yesterday. So I'm going to read the solution. It was quite a tough one. Took a lot of efforts. But today is very simple. Given two string arrays, return true if the two arrays represent the same string, and false otherwise. A string is represented by an array if the array, so we just concatenate them, right? Yeah, concatenate them. Concatenate string arrays. The string buffer, right? I think string builder. String builder dot append. Oh, I can just do that, right? Okay, so what is string builder then? What's the API for string builder? Is this dot append? Yeah, it's just dot append, dot append, dot append. Okay, so we just append then. Let's do it. Can we just compare string builder directly? That's a good question. Compare string is can we compare string builder? It does not compare the contents. I'll just get to the two string then. Compare two. Yeah, I'll just do compare to do the string. So we say string builder s1 equals new string builder, okay, and string builder s2 is also a new string builder, and then for string s of word 1, and I say s1 dot append s for string s of word 2 s2 dot append s, and then we'll return s1 dot toString dot equals s2 dot toString. Ooh. can be replaced by content equals. I never know this. See, this is dot content equals. Or, hold a second. Maybe we can just do, isn't this, wait. You cannot do the string equals, right? Compare string has to be dot equal. Yeah, it's a reference, so it has to be. But Java has something called content equals. Jesus. Contains the exact same sequence in the specified string or string builder. So why? Oh, it does not check if the other object is also an instance of string. Okay, so we do content equal then. So we'll do toString.content equal s2. Oh, I have to make. Nope. Nope. Why you always press? Oh, it's the real bad part is I still cannot type without looking. Like if you start typing, that's a different stuff, but without looking, I cannot. Learned about content equals in Java. See, that's something that I'll miss if you go with, you know, Vim or NeoVim. I don't think they will teach you, okay, there is a content equal. Let's see, the Java string builder. Compared to. They use compared to. 2 pointers. Oh, nobody used 2 pointers. All right, let's take a look. Math and recursion. Oh, it is a very difficult problem. It took me an hour and 20 minutes yesterday. It was yeah, a lot of efforts. We need to develop a strategy that allows us to set bits to 0. The first observation we can make is that other than the rightmost bit, a bit can only be changed with the second operation. Thus, if we want to change a given bit other than the rightmost to 0, we must first convert the number into the appearance. into the appropriate form. Yes, for example, if we have this in binary, if we want to unset the leftmost, we have to change it exactly. Let's start by considering the simplest case. How many operations do we need to reduce n to 0 and n as a power of 2? Exactly. That is 2 to the k plus 1 minus 1. We got that one already. But let's just read through the whole thing. If we have 2 to the k, where k is the number of the negative integers, yes. The 16. Yeah. So that's 1, 2, 3, 4, 5. So 2 to the 5 minus 1. We need to set the bit at position k minus 1. We use the second operation to unset. Now n becomes, so we'll set this to 0. Yes. New power of 2 and this step 3, the same problem. Yes. Both operations are reversible, exactly, because each of the two operations flip only one bit. If we can transform A to B with a single operation, it means we can reverse the process by applying the same type of operation to B and then flipping into A. Yeah. The minimum number of operations are converting x to y. For arbitrary x, y is always the same as the minimum number of operations to convert from y to x. There's a proof for that. I'll just skip it. But I mean, it makes sense, right? Because every step is reversible. Every single step is reversible. Because when you change the rightmost, you can change it both ways. And when you change because it fits the pattern, it's also reversible. So every step is reversible. So when you go from x to y, you can definitely go from y to... If x to y, you go through the minimum, right, the optimal path, then you can always go from y to x using the exact same optimal path. Reduce 2k to 0, or use this definition of f throughout the article. What is the value of fk? It will be the sum of the 3 steps above, yeah? So we start with step 1, k minus 1 bits to the right, all 0, then after, so step 1, set this, yeah. Step 2, costs 1 operation. This one is equivalent to converting 0 to 2 exactly. So this is a cost fk minus 1. Step 2, cost 1. The remaining is this. We're reducing to this operations. So fk is equal to this. Alright, so that is recursion. Base case f0 is 0. And if k is f0, yeah, f0 is, yes, f0 is 1. Yeah, this is 1. This is wrong. This is 1. So that is the fk. If it's, yeah. Yeah, this one you can, well, I have this 2 to the k plus 1 minus something. Yeah, because this is yeah, what's the mathematical term for this? a series with the same quotient, same ratio. Geometric. That's a geometric series. It's, dude, what did you do? It's a geometric series, right? It's a geometric series. You can compute it out. I mean, yeah, we can actually write it out. Let me see what was here. Right, so we say fk, right? Fk equals 2 times fk minus 1 plus 1, right? So we can say how do we prove fk? So we can say fk is equal to this, right? So fk minus 1 is equal to 2 times fk minus 2 plus 1. So we can put it in. So fk is equal to 2 times fk minus 2 plus 1. So equal to 2 to the squared fk minus 2 plus 1. Same thing, this will equal to 2 times fk minus 3 plus 1. So it'll be 2 to the third fk minus 3 plus 1. Right, so fk shall equal to, eventually will be k. So 2 to the k f0 plus 1. So if that's how it should be 2 to the k plus 1, which is the same as 2 to the k plus 1 minus 1, right? Yeah, so because your times, well, actually no, hold a second, that is not right. Did I get the thing wrong? 2 times, yeah, k minus 1. This is actually 2 to the 1th, right? Oh, I forgot a, oh, my bad. This is not right. Ugh, sorry. Forgot something very important. Very important. There's a plus 1 here. Alright, so it's 2 to the power fk minus 2 plus 2 plus 1. Right, and then it'll be 2 to the 3 fk minus 3 plus 2 to the 7. There we go. So equals will be 2 to the k f0 plus 2 to the k minus 1 plus 2 to the k minus 2 plus plus 1. And this is 2 to the k minus 1 divided by 1. Yeah. So, and then this will equal to, this is 2 to the k plus 2 to the k minus 1. So it's 2 to the k plus 1 minus 1. That is the result. So we got fk. It's just a little bit of math. That's fine. I use that. Where did you use that? Here. That's what I use it. But for me, I didn't really prove it for this. I simply, I feel it. Yes. Most significant bit, yeah. Then we can consider this bit on its own, and we have a value of 2 to the k. We know reducing this value will cost this. The remaining part will be all the bits to the right. Let's call the value of this remaining part this. And we can get this value as this equals n exclusive OR 2 to the k. Exclusive OR. Why would you do exclusive OR? Because you want to cancel out this. Makes sense. So you do exclusive OR, you get this part. So it will be fk plus any arbitrary x. Yes. I think the answer is fk plus an prime. However, it's actually fk minus an prime. Huh? Really? Yeah, that was my initial idea. You just do this and you add this, but it's not right. Because I mean the way I analyze it. Yeah, I have my way of analyzing it. It's slightly different. This is fk. 0 to this would take fk. That's correct. This to this would take this. So fk and then this to this will be answer. So fk will be, wait a second. Yes, this is equivalent to this. So fk will equivalent to an plus answer. Oh wow. Holy crap. Yeah, because it goes both ways, right? It goes both ways. So this goes there is fk. This goes here is fk as well. So fk consists of turning this into this, which is an, because it goes both ways. Now we have it. Yeah, then the recursion is very, very straightforward. You have this, you grab this, and you do fk minus this. Yeah, this is the main thing. If it's 0, return 0. Otherwise, k is the number of, how would you do? K is, I just need to know the length. And this is to, oh, you count length that way. Yeah, I guess it's fine. But I will probably just turn into a string. So you get the length, right? And then you know the total. Then you minus. Yeah. So hold on. So I would do it this way. Hold a second. Let's put it here. Let's renose this. So yeah, I absolutely hate this. Every time, I always by accident I will press proceed. Always accidentally press the wrong button. Always. Now Google has asked me to verify myself. Alright, we're back. I just accidentally pressed, I was going to press Control A, but I pressed Command A, I pressed Command Q. Alright, so we go 25J, right? Alright, let's go up. This will be 2. So this follows the official solution, right? Where it is shown with proof that a value 2 to the k will take 2 to the, I'll do this k plus 1 minus 1 steps to reduce to 0. But a more important conclusion is the proof that the minimum, the optimal, right, operations to turn x into y is the same as y into x, right? Thus, given any value n, right, give any value n, we can break it into 2 parts. The 2 to the k part, right, which contains the leftmost bit, and the remaining part. Okay. Let's call the remaining part is n exclusive or 2 to the k, right? Thus, let's call a n as the function that finds the minimum operations. Then an shall equal to 2 to the k plus 1 minus 1 minus a n exclusive or 2 to the k. Now here is the last important part, where we identify that an is the difference, not the sum of the two operations. Right. This is because the steps to go from 0 to 2 to n is the same as n to 0. Both are 2 to the k plus 1 minus 1. Right? Now to go from 2 to the k to n takes a n exclusive or 2 to the k. Right? Because this is the same as going from n exclusive or, let's go from this to exclusive or 2 to the k, the same as this 2 to the k to 2 to the k, right? Thus we have what? 2 to the k plus 1 minus 1 equals an right, equals an. An is, in fact, let's do this. Plus an is turn this, no, was an exclusive or 2 to the k plus an. All right, okay, let's do this. So if n is equal to 0, right? If n is equal to 0, we'll return 0. Otherwise we will convert k. K is binary, and we have to go length minus 2. That's k. So we shall return 2 to the, so we can just say 1 left shift k plus 1. Let's just do this. Minus 1 minus a, not a, self dot minimum this n exclusive or 1 left shift k. That's it. Solution is no solution. Exactly. Ooh, what happened? Memory exceeded. Wait, what? Hold on. Let's make sure everything works first. Nope. Yeah, 1 left shift k. And then at n exclusive or 1 left shift k. This should give me a smaller value. It's interesting. Is 3 now working? Oh, is this should be... No, it is a minus 2. It's a total length, right? If it's 4. 1, 2, 3. Oh, I think this should be k minus 1. K is the total length. K is the total length. It should be 2 to the... Wait, hold on. The number of bits, right? So it's 3. 1, 2. Okay, 1 left shift 3. What's 1 left shift 3? I'm confused. Right, 1 left shift 3 is 8. Yeah. Because... yeah, I was like wondering if we do shift wrong. 1, 2, 3. Put it here. So we have 0, 0, 0, 0, 1, 2, 3. Right? So, but this is 4. Ah, this is 4. This is 4. So essentially this is... k is number of bits, but this we can do 2 to the k, but when we do this, it should be just 2 to the k. And this should be k minus 1. Yeah, that was the reason. There we go. You know what? Let's make it more explicit. 2 to the k plus 1. Okay? And this is 2 to the k. I don't think it will be any different. 80 millisecond. Oh, I think maybe we should do this. No? Oh. We have to go shifting. My, I did not realize. 2 to the k will take too long. What's k? K is 9. I am surprised. Huh. That was all bit. All right. That was good. So this still has to be 2. I mean, we have to go up here as well. This should be 1. All right, that's just one solution. All right. Iteration. We're not gonna do iteration. Recursion is much easier. Gray code. It's very advanced. You should not be expected to derive this approach in an interview. We have included for the sake of a gray code. Frank Gray. What is a gray code? A reflected binary code. What? Two successive values differ in only 1 bit. I have heard of this. Oh. Error correction, yeah. Touched upon it. I heard of it during the class. Wow. It's all right, gray code. So we order them so that successive number ordering differ by only 1 bit, which is exactly what this is. Successive differ by only 1 bit. The two operations are capable only of changing exactly. Yes, thus any sequence of numbers generated by these operations must also be a gray code. Okay? There can be many gray codes. The standard encoding actually follows the exact same ordering as one that will be produced by the operations. Oh, that's where they got the idea from. They saw gray code and they're like, how do we do that? Ah, so there's the rule for gray. Oh, so this is the rule to produce gray code. This is the rule to produce gray code. You either change the last bit. Yeah, you change the last bit. And that will differ by 1 bit. Or you change the bit whose right neighbor is a 1, but everybody else is 0. So that's the rule. That's the rule. So the problem just reversed it. Holy guacamole. This problem is actually equivalent to finding the index of n in the standard gray code sequence that starts from 0 exactly. I think I saw that thing, that bunch of exclusive or here. Gray code 32 bits or fewer through the use of SWA. A parallel prefix function. The assignment statements can be in any order. So what does this do? The follow function converts between binary numbers and their associate. Oh, a gray code is the order where you are on the gray code. It may seem that gray to binary conversion requires each bit to be handled one at a time. Faster algorithm exists. Ah, so the gray code is, this is your gray code, right? No, these are the numbers. No, these are not numbers. These are the gray code. There's a 0. Gray code 1 is 3. Gray code 2 is what's that, 6, right? Gray code 3 is this. Where is 2 then? That's not right, right? What is 1, 0? I don't see 1, 0. I have 0. Or is the last one doesn't count? Oh yeah, I think the last one doesn't count. It's just this 0, 0, 0, 1. Yes, 1, 1 is 2, 1, 0 is 3, exactly. And then this is 4. This is 5, yes. This is 7. Ah, so then you just want to find the where it is on the gray code. So you just use this. Very efficient algorithm to do this. Yeah, I'm not interested, but it's absolutely bonkers. Oh. Yeah, I'm just copy and paste this. I don't even want to implement it. And what's the point, right? The gray. Did I spell it right? Is this gray, right? Yeah, code solution. My suspicion is that, well, the operation is exactly how gray code finds its next binary value. My suspicion is that whoever wrote this problem looked at gray code and simply thought, wouldn't it be fun to count the steps that goes from one value to the other via gray code. It's fun. I don't think it will be any faster though. It's actually not, because this like when you have right shift 16, I don't know, right shift 16 and then exclusive or anyway. All right, so we're done with this. Good, we can turn it off, and that will be it. I'll see you guys tomorrow. Adios.